Hey everyone, and welcome to Revealing the Power of Legacy Machine Data. My name is Oliver, and I'm happy to take you on a journey about dealing with legacy machine data at ENGEL. But before we start off, I would like to give you a small introduction about ENGEL first. So ENGEL is Austria's largest machine manufacturer, and we focus on building our injection molding machines. And we're also the market leader for injection molding machines. One might ask, what are injection molding machines? So basically, injection molding machines are the machines that are used to produce plastic products. ENGEL is set up in 5 different business units. And we start off with automotive, where, for instance, you have in your car panels and so on. These kinds of things can be produced by our machines. Then we have the medical area, packaging, technical molding, and also teletronics, where our machines, for instance, produce frames for mobile phones or even TVs. To set the scene, we like to talk about the ENGEL customer service. So our customer service works in the following way. The customer calls our hotline, so this is our first level support, when he has a problem with our machine. The first level support then tries to solve the problem on the line. If he can, then it's fine. Then he can close the ticket immediately. But if he cannot solve the problem immediately, he has to send a field engineer at some point. The field engineer is then advised to collect so-called error reports that we use to analyze errors on the machine. So the field engineer and the first level support are in constant communication and trying to fix the problem. This mostly only happens if we have a more complex problem that's related to more analytic stuff and so on that we really need to investigate. So when our ENGEL headquarters team has finally solved the problem or identified the problem, he's then able to guide the field engineer to solve the problem at the customer's site. And this whole process is documented in our ticket system, where we also link these so-called error reports. And back then, all these analytics were done using Excel. So Excel was our main tool of choice at ENGEL back then. Everything was done using Excel. We were not really using any classified data. It was just a whole mess of data that we worked through with Excel. So in there, they were able to compare parameters. So if there were any wrong settings at the machine, then the service engineer can somehow derive if there's an issue on the machine related to these parameters. But it might also be the case that the machine was just under such high pressure that it simply broke down. And this is where we had an idea that we could use to actually centralize all the data that we have with these error reports in one place and use one central analytics tool or a so-called DIY tool that we can then use to solve the problems in need. And this is where we thought, why not simply use a central self-service tool that everyone is able to use? So for instance, if the customer has a problem, then he can upload a report to this self-service tool. If the first level support identifies a problem, he can also solve the problem on the line, or even the field engineer if he wants to. So this is our main use case where we want to assist our customer service. So we are built here on 3 main pillars. So the first one is that we want to use data scientific methods to assist our customer support. So with these error reports in our ticket system, we have a classified error documentations that are attached with symptoms, errors, and solutions that we can use in future to automatically infer the errors that actually happen on the machine. Thus, we can reduce maintenance and repair times and also try to predict future errors using live data, for instance, and also discover serial defects in an early stage and inform our customers directly which machines are affected. And last but not least, probably one of the most important things is that we want to generate a sustainable knowledge base. With that, we can ensure a fast onboarding process of new employees since we have this self-service tool that they can use to solve the problems, and they can focus on fixing the problems efficiently. And on top of that, of course, we can use this data source to build data-driven solutions on top of it. And this is where we started off. So basically, our data was distributed anywhere around ENGEL. So we had several mail servers, we had network shares we had network drives, we had central servers, we had SAP, we had Hadoop. So basically everything was distributed. And this is where we started off and tried to somehow think of a solution where we can centralize the source of data to make it accessible for everyone. Because in this current setup, it was definitely not possible to search for a specific status report on a specific ticket case from our customer support. So this is where we needed to do something. And before we go into details about how we centralize this, I want to give you a more detailed insight of our status reports themselves. So basically, such an error report or also status report is a zipped collection of serialized log files, where log files may be the snapshot of the machine's parameters, so the settings that are configured at the machine, but also, for instance, a log file which contains the last 10 errors on the machine, and many more different log files. And we mainly use these error reports for fault discovery and also for documentation purposes. So as I've already mentioned before, our service engineers can make use of these error reports to read the errors from these reports if they're able to, and if they can find the errors, then they can also provide a solution on top of it. And last but not least, we have been collecting these error reports since 1990, so this data format has definitely grown by a lot. And it started from a simple text file and is now ranging from zip files to TGC files, and everything that you could imagine is being stored in these status reports. And then these newer versions of these error reports, we have a recursive archive structure. So we have zip files and zip files, and then again we have zip files. So it's a very heavily recursive archive structure that we have here. And then this archive structure, we can find log files, which most of them are binary serialized. So we have some kind of custom serialization that was used to serialize the log files. And most of the time, non-standard tools were used. So there is nothing like Afro serialization or Parquet or anything else that you can imagine, like Cryo. It was just plain custom binary serialization that you have to write a custom algorithm to be able to deserialize the data first. Then we have memory dumps and also the parameter snapshots. And in the image on the right-hand side, you can see such a parameter snapshot, which contains a collection of all the variables that are configured on the machine, grouped by their corresponding components of the machine. So we have several root nodes where, for instance, this air pressure monitoring one has several variables beneath it, and we have intermediate nodes, and then we have the leaf nodes, which are the actual variables. And this is our parameter snapshot file. But I will get back to this file at a later stage. Let's now talk about the issues that we had with these error reports. Since it's such a data source that has historically grown by a lot, we've now accumulated about 13 different timestamp formats that we have to deal with. And on top of that, as I've already mentioned, we have a different structure for each controller generation on the machines we have. So as I've said, we have text files, we have zip files, we have TGC files, everything that comes into your mind. And then in the next stage, you discover that you have 13 different timestamps formats. So you can imagine how difficult it is to automatically process this kind of data, especially when there are broken archives because the error report was not successfully drawn, might be due to a software bug or anything else. And also we have missing files and many other different things that we had to handle first to be able to process this kind of data. So which tool is able to kind of deal with this data? This is what we were thinking at this stage. And then we discovered that there is one software stack in the field that we could use. It is Hadoop. Most of you are probably familiar with it. And Hadoop back then was very much in fashion. There was Hortonworks Dataflow and Data Platform that was very promising at first. And it had our core components like Apache NiFi, Spark, Kafka, and HDFS that we were using as our core components. And we immediately started off to prototype it on a Raspberry Pi cluster. So we had five Raspberry Pis that we were using to set up a basic cluster, and we tested our pipelines on there. And yes, it worked really well, and we were able to run it on this Raspberry Pi cluster. So why shouldn't we deploy it in an established on-premise environment on dedicated hardware in an on-premise environment? And this is what we did next. And here we have our initial prototype of our initial data flow solution. So the first pipeline that we introduced that was also used in the first production scenario. And what basically happens is that the service engineer uploads his report via a third-party tool through a REST endpoint to Apache Unifying, which we use as a data ingestion and routing tool. So what Unifying does in this case, it simply writes the data to HDFS and also writes to Kafka. And the reason why we write to HDFS and Kafka is because Kafka on its own is not able to handle such huge files that we have with these error reports. Because one error report can contain up to 30 megabytes, it is not really reasonable to store this kind of data into Kafka. That's why we simply put the file path into Kafka and then read the data back from HDFS. And from Kafka onwards, we were able to stream using Spark streaming, where we had 2 Spark jobs, where one was responsible for processing the metadata about these error reports, and one was responsible for processing these parameter snapshots, as I've shown you before. We use HBase as a serving layer and also our HDFS using Spark applications to serve BI, web, and mobile apps that you can see here. And of course, in this architecture, as there is always problems, we also discovered some difficulties that we encountered here. So first of all, we had to maintain streaming and batch jobs. Since we have so much historical data in this use case, we somehow need to process or reprocess the data very much. And this leads to our kind of Lambda architecture, where we have to maintain both batch and streaming jobs. Then, of course, we had the Kafka and the large files problem, as I've already mentioned. This led to kind of a workaround in our Spark streaming jobs, as you can see on the right-hand side. So we first read the JSON from the Kafka topic. Then we read from the Kafka topic the file path to HDFS. And then from HDFS, we were able to read back the data into an actual RDD. And also, again, here we had to use RDDs because Spark 2.x was not really able to support binary files without using the RDD API. So this was also one drawback that we found here. And then after the Kafka and the large files problem, of course, we discovered the Hadoop and the small files problem. Because Hadoop is not really able to handle small files, that's why we had to kind of write a repartitioning job that takes the small files and merges them together to bigger files. And so this is kind of the opposite problem that Kafka has. So Kafka likes small data and HDFS doesn't like small data. So this had to be treated. And of course, there is this problem with legacy binary deserialization, where we had to use custom libraries that are written in Pascal. And yes, I really am talking about Pascal here, that we have used with JNA to attach them to the Java virtual machine and use them in a Spark job. And of course, this was not the only difficulty to understand Pascal. So it was also very troublesome to make Pascal work with the parallelism of Spark. So this was another layer of difficulty that was added here. And lastly, there is this unpredictable parameter snapshots. So the parameter snapshots, I also like to call them memory bombs, because some of them are 2 megabytes of size on disk, and then they unfold to up to 800 megabytes in memory or also on disk. And this is per report. And it also varies very strongly. So we have reports maybe from the older generation where we only have 200,000 variables, but the newer ones also contain up to 3 million variables per report. So this was also very challenging, and we also had to deal with this kind of data to store it. And we didn't really find a suitable database that was able to deal with this data. And this is where we went this classic data lake approach, and where we simply stored the data as Parquet files in our HDFS. And for that, we didn't really use the tree structure because it's not really useful to navigate through this tree and for this use case. So we had to flatten the tree. We simply concatenated along the tree to the leaves by using dots and the variable name. And in the right image, you can see how the final structure looks like. So we have some metadata attached to these variables, and then we have the real values and also the units for these variables. So we needed to partition these system variables, as we call them also. We thought at first, why not simply group them by the machine's components and simply partition by that, because that's what usual machine manufacturers would think of. But in this case, we were not really able to do so because it led to a very heavy skew, because some of the machine's components only contained 10 variables, while others contained about 100,000 variables. So it really varies from the machine components. And we had to search for a different solution in this regard. And this is where we invented our custom hash-based partitioning function, where we simply took the first 3 parts of the variable name. So we could easily split by dot and just take the first 3 variable part names and simply hashed it using an MD5 function. And then we were able to use the output of this function to assign partitions to the corresponding variables. So this is kind of a particular use case because we're not really talking about time series data. And most of the time, when you talk about partitioning, you see the typical partitioning scheme by date and also month and so on. But in this case, it's not really time series data. It's just data that is drawn on demand. And we simply had to deal with it. And this is where we invented this hash-based partitioning function. It turned out to work really well. We had very balanced partitions, but the only issue we faced is that regex queries and also queries that asked for multiple variables of the same machine component were not very efficient, because then we had to again search through multiple partitions because of the hash's randomness. And this is where we had to think of a different solution, because there the efficiency was really lost. And we had to search through all partitions in these use cases. And after all, this architecture didn't really work out well for us. So we discovered many issues that we had. Here are only some of them. So first of all, when using Hortonworks, you have these big data big bang upgrades and migrations, where you simply have to upgrade the whole software stack or nothing. Apart from that, it wouldn't work. And this is where we had our troubles, because nobody really had the know-how on how all of these tools in this software stack actually work. So this was not really reasonable for us, and migrations took a very long time. Secondly, job monitoring was basically non-available. One excuse for us might be that there are so many software components running on this Hadoop stack that we were not really able to distinguish how the resources were divided between these different software tools. And it was really hard to set up a monitoring. That's why we had basically no monitoring, which is also very fine if you think of it. Then we had to write the repartitioning job. The repartitioning job is responsible because of the Hadoop small files problem, where we had to reconcile all the small files into bigger files so that our Hadoop name node doesn't get too much pressure from all the files that we store in there. And as you might already guess, when using such huge batch jobs that process 180K status reports, where we have this high memory pressure because of these parameter snapshots, you can imagine of how many out-of-memory errors we got, as you can see on the right image, where we always should boost the yarn memory overhead. And we always boosted it, and it simply didn't turn out to work, because in the end it always failed. And of course, if the task was running 30 hours, it would fail at the 29th hour. So this was really cool to debug and to fix the problem. It was a really time-consuming process. So after all, this whole architecture felt like a big workaround, and we thought there must be a better way to actually solve this architecture. There must be someone who supports this use case. And this is where we started to think of the cloud, and the cloud as a possible solution. And this is where we are now. So we have migrated everything to the cloud, which would be a topic for a talk on its own. But let's keep it at that. And again, here we have our field engineer who's uploading the report, again, to Apache NiFi, now running on Kubernetes. And NiFi simply stores the data now as a blob on the Azure Data Lake storage. And here comes the cool part, where we don't need Kafka anymore. We can simply use Databricks and the autoloader feature to stream from our data source. And we don't need to listen to Kafka and then read from HDFS again. So this was all removed by the very great feature of autoloader. And then we only had one Spark job left. We simply merged the remaining 2 Spark jobs into one, and used Cosmos DB as a serving layer, and also Delta Lake with Databricks Spark to serve our BI, web, and front-end apps. But how are we dealing now with these system variables that I've mentioned before? So basically, we wanted to be able to query by the machine's components. And this is where we had to think of a different partitioning scheme. So I call this the equidistant range partitioning scheme. I'm not sure if there's an official term for that. But what you basically do is we sort the variables, and then we cut off after a specific variable and move the next variables into the next partition and so on. So for this to work, of course, we had to first initially determine the number of variables that belong to each partition. And we had to create a lookup map so that we were able to assign each variable to a partition. And this is how it worked out. And in fact, it works out very well. So we are now able to issue regex queries and also do these component related queries, but also point lookup queries are still as performant as before. And of course, we are now able to use Databricks optimize feature and C ordering. So we didn't really have to write a repartitioning job anymore in the cloud. Everything was solved by using Databricks as our Spark environment. To work towards an optimal solution. So are we really speaking of an optimal solution right here? For the moment, I think we are speaking of one because we have reduced our complexity by a lot. We now only have one configurable Spark job that can deal everything. It's only one streaming job, so we kind of unified the batch and streaming paradigm where we simply can use autoloader to stream from the Azure Data Lake storage. So basically, we were able to use the Kappa architecture, if you want to name it. Then we were able to ditch Kafka completely. So we had one dependency less to maintain, which is also quite nice if you think of it. Then we had reduced memory pressure because of this whole streaming architecture, and with Spark micro batches, we were now able to reduce our memory pressure by a lot, which for this use case is very essential because we have these memory bombs and we simply had to deal with it. And by using micro batches, this problem just fades away easily. So this in general led to more stable jobs in our environment. And lastly, we finally had monitoring for our Java virtual machines and the ganglia matrix that I love so much from Databricks. So this is very handy, and I can only recommend these ganglia metrics. They are really useful to actually see the pressure on the virtual machines behind the Spark environment. To get back to the use case at ENGEL, so the current state is that we have established several self-service tools using these pipelines, as I've just mentioned. Here you can see one dashboard that we've created where our service engineers can see the overview of all status reports that we have. And we are also able to send a PDF summary to our field engineers with the relevant steps that they could take to actually solve the problem at the customer site immediately. Or he could also include other things that he could also fix on the machine, for example, clearing the memory, clearing the log files, and so on. So basically a summary of steps to improve the machine's health state. And in future, we also want to use these error reports with our connection to the ticket system to actually learn from the data with the fault history and so on, so that we are able to, when a user uploads a report, we're able to automatically detect and classify the error and send back the possible or the relevant steps that our field engineer needs to do to solve the problem at the customer. And before I close this talk, I would like to leave you with a few points. So first of all, do never underestimate the effort that is put into process legacy data. The unknown is just too daunting. So many unforeseeable things will happen. So we never knew in the beginning that there were 13 different timestamp formats. But legacy data just grows historically so much that you have so much history in this data and so many different engineers that have worked with this data, and this just whole thing grew so much that we are now at this state that we are able to deal with it, and I can now work to improve it in future. Secondly, the change management to actually use this centralized approach and have these DIY error analytics tools that everyone can use is very demanding. So it's a time-consuming process that you need to live through in the whole ENGEL culture. And I think we have finally reached a point where we have achieved this, and everyone is currently seeing the benefits out of this architecture that we have now, and that everyone is able to access the data. So these self-service tools are now really understood by our company. and they're really favoring it to the previous solution because they can now see all the reports that they need. And then, of course, we have the unmanaged cluster thingy. So it was just pure frustration for us because we developers had to maintain the clusters on our own. And this is not a task that we should do. We should focus on developing applications on top of our data and not really spend our time with maintaining the current jobs that are running on our infrastructure. So I definitely do not recommend that you as a developer try to maintain such a cluster. It's just pure frustration. And of course, this whole complexity was then removed by moving to the cloud where we have fully managed services. And also Databricks helped us a great deal in setting up this whole pipeline, and everything seems to work out quite well now. All right, and that's it from my side. I'd like to thank you very much for your attention. My name is Oliver, and please do not forget to leave some feedback. Thank you. Bye.